All right, I think we'll start. So Imogen, if you can give me, don't let me go over 15 minutes.
Okay, do you want me to put a timer on my phone?
Yeah, on this side.
Yeah.
And if we run out, if we run out of questions, then we'll run out of time before we've got through all the questions. That's not a problem.
Okay.
Is that all right?
Yeah. Cool. All right, so let's go. So Ed, how do drugs work?
Okay, so drugs can elicit their actions via one of 4 main mechanisms. Okay, so the 4 mechanisms are either through the physiochemical properties of the drug. They can exert their actions through interactions with voltage-gated ion channels, through interacting with enzyme systems, or through interacting with receptors. Okay, so an example of a drug type that exerts its action through its physiochemical properties would be, for example, the neutralizing antacids, so things like sodium citrate. Another example would be Gamadex, where its 3-dimensional structure selectively binds rocuronium and relies on that property to work. Drugs that exert their effect through interaction with voltage-gated ion channels would include, for example, the local anesthetic agents and a number of antiarrhythmics. Drugs that interact with enzyme systems could include ACE inhibitors or neostigmine, and there are a variety of different ways that drugs act on receptors. Perhaps we can talk about those shortly. Okay.
And what's a ligand?
So a ligand is a substance that binds to a specific site on a receptor and elicits a response.
And how about a receptor?
A receptor is a protein that is usually membrane bound, but not always, that has a specific binding site for a ligand to bind to, and when bound, elicits a response within the cell.
Great. What governs drug-receptor interactions?
So drug-receptor interactions are governed primarily by the law of mass action. So this states that the velocity of any reaction is proportional to the concentrations of the reacting parts. So for a reversible drug-receptor interaction, you typically have drugs and receptors, and it is a reversible reaction, and there's an element of equilibrium between the drugs and receptors being separate and the bound state of the drug to the receptor. So the velocity of each stage of that reaction depends on the relative concentrations of the reacting parts. Okay. So the velocity of the forward reaction, i.e. the drugs and the receptors binding to each other, is determined by the concentrations of the drugs and the concentration of the receptor, and the the concentration of the association constant. So K1 is what that's termed, and that's the affinity essentially. So how avidly the drug and the receptor bind, how well matched they are. And then conversely, the backwards reaction, so the dissociation reaction, is determined by the concentration of the drug receptor complexes and the dissociation constant.
Okay, good. What are the main mechanisms of receptor action?
So when a ligand binds to a receptor, there are typically 3 sort of ways that it elicits its change within the cell. So it can alter membrane ion permeability. It can enact its action through second messenger systems, and there are a few different classes within that. Or it can alter or regulate gene transcription.
Do you want to could you give me some examples of each of those?
Absolutely. So an example of a drug that would alter ion permeability, or a ligand that would alter ion permeability, might be, for example, the nicotinic acetylcholine receptor at the neuromuscular junction. Or another example might be the actions of GABA at the GABA-A receptor. Okay. Drugs that alter gene transcription, these tend to be intracellular receptors. So they tend to be lipid-soluble molecules that have to traverse the cell membrane to get to these, and they tend to be things like steroid hormones or thyroid hormones. Okay. And then the receptors bind to the drug in the cytosol of the cell and then move into the cell, the nucleus, and exert their effect on DNA transcriptase.
Okay. Can you tell me about G protein-coupled receptors?
Okay, absolutely. So G protein-coupled receptors are a cell membrane bound transmembrane protein which has a serpentine structure, i.e. it traverses the cell membrane. So if this is the cell membrane, It traverses the cell membrane 7 times. On the exterior of the cell is a binding site for a ligand. And on the interior of the cell, it is coupled to a G protein. This transmembrane protein is coupled to something called a G protein. A G protein is a heterotrimeric protein, so it is composed of 3 different units. It is composed of a beta, a gamma, and an alpha subunit. And the alpha subunit is bound in the inactive state to ADP, adenosine diphosphate. These receptors are classified based on the specific subtype of G protein to which they're associated. And this is dependent on the alpha subunit. There are 3 types that we commonly classify it into. So there are inhibitory, so GI proteins. There are excitatory or stimulatory, so GS proteins. And there are sort of slightly atypical ones, which are referred to as GQ proteins, which I think of as GQ for queer. And each of these has a different effect. So do you want me to talk a little bit about what happens when they're bound?
Please do.
Okay. So the binding of a ligand to the extracellular side of the receptor here results in a conformational change of the transmembrane protein. This results in the activation of the alpha ADP subunit, the alpha ADP dimer. This causes the binding of ATP, adenosine triphosphate, to the alpha subunit, which then the alpha and ATP subunit dissociates and moves away from the rest of the G protein. This then goes off and has an effect on a second messenger system within the cell. And that effect is dependent on what type of G protein it is. So for a GS protein, a stimulatory protein, it will go off and it will stimulate adenylyl cyclase enzymes, which will increase your intracellular levels of cyclic AMP. And then the converse is true for a GI protein. So it's an inhibitory protein, so it goes off and inhibits adenylyl cyclase and reduces intracellular cyclic AMP. GQ proteins are referred to as queer or different because they act on a different second messenger system. So when the alpha ATP subunit moves away, it actually interacts with phospholipase C inside the cell. Phospholipase C inside the cell then goes on to activate to increase levels of IP3 and DAG within the cell, which have effects depending on what that cell is. Once it has activated its second messenger enzymes, the alpha subunit actually acts as an ATPase enzyme in its own right. So alpha is bound to ATP and will then phosphorylate the ATP molecule, resulting in the reformation of an alpha and ADP, so it loses one of its phosphate ions, so you get alpha ADP rejoined, and an organic phosphate molecule as a side effect. The alpha ADP subunit, which is the original state it was in, then is able to go back and bind to another G protein. When a ligand binds to a G protein on the outside of the cell, it can activate more than one G protein on the interior of the cell. And each G protein on the interior of the cell can also activate multiple second messenger enzymes. And so for this reason, G protein-coupled receptors are referred to as exhibiting signal amplification. Ligand binding can result in a large number of second messenger systems.
Great. And compared to the other types of receptors that you mentioned earlier, what speed do the G protein-coupled receptors act at?
So G protein-coupled receptors are slower to work, generally speaking, than the receptors that interact with the cell membrane ion permeability, but are faster to act than receptors that rely on gene transcription to accept their effects.
Good. Do you know of any other mechanisms by which drugs might affect cyclic AMP?
So cyclic AMP is broken down by phosphodiesterase enzymes. And so phosphodiesterase inhibitors, such as milrinone, phosphodiesterase inhibitors will decrease the activity of the phosphodiesterase enzyme and therefore will increase cyclic AMP in the cell by an alternative mechanism.
Okay. Which system is mainly affected by drugs? altering CAMP levels.
Which system is?
So what system are milrinone and aminophylline acting on?
Oh, so cardiovascular primarily.
Sure.
So yeah. So for example, drugs that work on protein-coupled receptors include drugs that act on your cardiovascular system. So all of your alpha and beta receptors are G protein-coupled receptors, and the opiate medication. Opiate drugs also act on G protein-coupled receptors.
What effects may a drug have upon binding a receptor?
A G protein-coupled receptor.
Any receptor.
Any receptor. Okay, so a drug may bind to a receptor and elicit either a response that is the same as the receptor would elicit from a normal natural ligand, i.e. it sort of exhibits an agonist effect. It may exhibit an opposite effect to what the natural ligand would affect, i.e. an inverse agonist, or it may exert a sub-maximal effect. And there are two types of drug that would do that. So there's an antagonist is a drug that will bind to a receptor, i.e. it has affinity for the receptor, but it does not produce any response at all from the receptor. It lacks any intrinsic activity. Or you get something called partial agonists, and partial agonists are drugs that bind to a receptor but elicit a sub-maximal response from that receptor.
Good. I think that's all of the questions. Okay. There, got through all of that.
Thank you. Cool. Thank you so much.
Good.
Brilliant. I'm doing 3 minutes left. Brilliant. Good.
Yeah.
Okay. Thank you very much.
That's all right.
Okay. So, like last week, a little run through, and then if you guys are happy, we'll do some MTF style practice. Is that right?
Yeah.
Same topic?
Good. Yeah.
Good.
Yeah.
So I'll just get them fired up on the screen.
Cool.
Right, so we'll do the same as last time, and I'll just bring them up on the. I'll bring them up on here. Oh, the screen's gone down again. I don't know why this bothers me so much. Right, so hopefully you guys will see in a minute a QR code you can scan to do an online MTF calling thing.
Nice.
We'll see. What's that you expecting to know?
2 o'clock.
Oh, mate.
I know. I had way too much coffee this morning, so like the anxiety just was made so much worse.
What's your gut telling you?
I honestly don't. I really don't know. That
So,
on the day, I just thought it was awful.
People at home, you can obviously scan this code as well and try and join in with the questions. It's nice to have you joining in. And if you guys, when we do run through answers and stuff, if you do know them, drop us a text or something to let us know you want to chip in with volunteered answers, and you can put yourself on loud. Join in the fun. Good. Okay, so that should hopefully, that QR code should bring you up the questions in a minute when I activate them.
Hopefully, if you found it really hard, other people would have done as well.
Yeah, hopefully.
Okay, well, we'll crack on. And I'll just. Have I opened photo? No, I haven't. No, I haven't. Sweet, okay. Should we have a little chat through these, and then everyone else who's joining along can help? So what did everyone say? I didn't show the results last time, so we can do the results showing this time. Grand. Nice spread. And a lot of voting there. Cool, so I reckon that all of these things are true.
Okay.
And some of them are easy and some of them are hard, sorry about that. So following the activation of G protein-coupled receptors, signal amplification, look at it, everyone thought that was true.
Yeah.
Why is that? Anyone?
Because the alpha ADP subunit can activate lots of other cell messengers, not just one.
Yeah, absolutely, yeah. And actually each...
Does it also go back?
but that would require reactivation, wouldn't it? So this is just following activation. But it's each alpha ATP subunit will activate multiple second messengers within the cell, but also each ligand that binds to the exterior side of your G protein will activate multiple alpha ATP subunits.
Yeah.
There's two different stages at which signal amplification occurs following the binding of your ligand. IP3 causes calcium release in the plasma reticulum. Either that's sort of, I'm afraid that's one of those things you know or you don't. The mechanism of action of IP3, and DA activates protein kinase, the mechanism of action. Sorry. DA activated protein kinase. What happens after that does depend entirely on the cell. So that's all you'll be to expect to know as a sort of a general overview thing. IP3 causing calcium release, I think, is universal, but it doesn't matter. Mitosis can occur. True or false?
That strikes me as one of those never always kind of questions. I think it can.
Yeah, can.
It's a,
Cans are often true, aren't they?
yeah.
Not always, but cans are often true.
So that would be a muscarinic. Oh, hang on. Meiosis is contraction, making smaller, which is parasympathetic. So it would be a muscarinic action.
Alternatively, opiate action.
Pardon?
Alternatively, opiate action.
Oh yes, yeah.
So you get towards the end. I think I tried very hard to make sure that I said at some point that opiate receptors act via G protein opiates act via G protein coupled receptors, and meiosis obviously an effect of opiates. So yeah, absolutely. The alpha GTP subunit dissociates from the beta gamma dimer. Sounds like a really scary sentence. There are lots of really technical things in there, but it is just describing that molecule that I try my best to draw on the iPad.
Yeah.
Grand. Okay, so that's that one. Happy to move on?
Yes.
Regarding drug receptor interactions.
So we're meant to take everyone that's true.
Everything is
Yeah.
true, so it's a multiple true false, yeah, sorry, that's lack of clarity. Sorry. Brilliant, so we got 4 answers back. Right. See what people have said? Let me see that. Okay, so regarding drug receptor interactions, a partial agonist has significant affinity and an intrinsic activity of between 0 and 1. That is the definition of a partial agonist, so it doesn't produce a maximal response from the receptor. So what effect will a partial agonist have when it's given?
So if it's given alone, it will have an agonist effect, but just submaximal. If it's given with if it's given with a full agonist, it will have an antagonist effect because you're actually not going to get, because the agonist would give you the 100% effect, but if you give it with the partial agonist, that will only give a smaller effect. Therefore, overall, you're going to get an
Yeah.
You're also blocking receptor sites, aren't you? With the...
Well, you're not. It sort of acts like you are, but you're not. You're occupying them and you're eliciting a response. So the key thing with what you said, like 95% true, that we need to emphasise there is that it's with giving high doses of an agonist. So if you give low doses of a full agonist and low doses of partial agonist, they'll still probably likely have an agonist. And once you start getting to high doses of your full agonist and you're giving a partial agonist as well, Then you get to the point where there are a limited number of receptor sites available, the two are competing,
Yeah, okay.
and so the partial agonist will stop your full agonist from occupying all those receptors, so you'll never be able to elicit the full response.
Yeah.
Because some of those receptors only give 50% response.
Are we allowed to close the door?
Yeah, please do, yeah.
Okay.
Sorry, it's quite loud, isn't it? Graham, increasing agonist doses fully overcome the effect of a competitive antagonist.
Yes, because it's competitive.
Yeah, absolutely. Yeah. Certain drugs may produce an effect opposite to that of an endogenous agonist. Anyone got an example? Anyone at home? Oh, talking like that, me.
Well, I guess, I suppose you could argue that any anti-hypertensive has the opposite effect to our the endogenous agonist of adrenaline. Like, is that what it's saying? Like,
No, so this is about, so certain drugs may produce an opposite effect to that of an endogenous ligand would probably be a better way for me to phrase that.
Okay, I see.
So this is talking about, the classic example is atropine and acetylcholine at the muscarinic receptor have opposite effects.
Okay, yeah.
So that's your classic thing. So it's not just that atropine is a blocker, atropine also has inverse agonist effects, and so that's the one that they tend to talk about with inverse agonism.
I see, okay.
An antagonist has low affinity and high intrinsic activity.
False.
Yeah.
It's got affinity, but it has no intrinsic activity.
Perfect, that is the definition of antagonist. It's worth remembering. And it's worth them getting a good clear idea of the terms affinity, which means how avidly the drug binds to its receptor, how well the key is locked, as the next podcast puts it, and intrinsic activity is the response that is elicited once bound. So an antagonist wouldn't be very useful if it didn't bind, would it?
No.
Yeah.
So what it does is it binds and stops everything else binding and having an effect. So it just blocks it. It's like parking cars parking space. And then a less potent drug is likely to have a quicker onset of action.
Yeah, I said false to that.
I think it's true, because if it's less potent, you give it in a higher dose, which means it's in a higher concentration.
But I'm
at the
assuming that
receptor.
you're giving it at a higher dose. So the question doesn't say you're going to give it at a higher dose.
I wrote the question, I thought it's true. I can see your argument, but typically, so there are two examples that this demonstrates. So one of them is rocuronium and tricurium. So the reason that we give rocuronium such a high dose for rapid sequence is because it has a quicker onset of action at really high doses because it's less potent. So that's why we give it. That question comes up a lot in NTFs.
There's a term for it, isn't there? It's the something effect, but I can't remember. It's got like a name. I can't remember.
I have no idea.
Yeah, no, that's okay.
And there's the other sort of one where this comes up is alfentanil. So there's two reasons that alfentanil has a quick onset of action, but they both essentially equate to having a higher concentration gradient across some membrane, and that is partly because it is less potent, so you have to give it in high doses, and it's partly because it is more unionized than fentanyl is. So that's why it's quick to work. So yes, it is probably true. So a less potent drug is likely to have a quicker onset of action because of something called the ED50, effective dose of 50%. And in order the effective dose of 50% is higher, i.e. your log dose response is shifted to the right in less potent drugs. And so to have the same clinically effective dose, you have to give more of it. So you're going to have that higher concentration gradient so it'll be quicker. So I think that's true. Happy?
Yeah.
Cool. Should we do the last one?
Yeah.
I'm going to finish on time this time. Should we start talking it through?
Yeah.
Regarding the log dose response curve height is always less for a partial agonist than a full agonist. True or false?
I think that's true.
You think that's true? I think it's true. It's suspicious, isn't it? Always.
Yeah, exactly.
I really wanted to write a question where I could say always where it's true. That was my one objective today.
Yeah.
So having said that last week,
was
to make sure I could write a question. It is true. I think it's true. Yeah, good. Why? So what is the log dose response curve?
So you have then the log dose and response on the y-axis.
Yes, exactly.
And it's I've forgotten the shape of it.
Do you want to draw it?
Why I think yeah.
Do you want to draw it on here? Do you reckon you can do it on here?
Yeah. Thank you.
So it should just be finger.
Cool. Yeah. So your y-axis is response. Your x-axis is log dose, I think. And it looks like, sorry, that shouldn't be that flat at the top. But it looks like that.
Not hard to examine it. So that is a sigmoid shape.
Sigmoid. That's the yeah.
If I was to ask you to draw the dose response curve, would you be able to do that?
Okay. Right. Let's try. I can at least do this bit.
Yeah, or maybe a bit more so.
Dose response. So if by logging it you've got a sigmoid curve, then unlogging it, is it exponent? No, it's not exponential.
It looks similar. It looks similar to a positive exponential curve. It's a rectangular hyperbola.
Which means it's okay. So hyperbolas never cross the axes. Or do they? They do.
Hyperbola mathematically is a conic section, so it's a slice through a cone.
Yeah. So it's not.
Just think about it logically, right?
Yeah.
I give a dose of 1 milligram of a drug.
Yeah.
It has a little bit of an effect. And I give a dose of 2 milligrams of a drug.
Mm-hmm.
It has a little bit more of an effect.
Yeah.
And I give a dose of 4 milligrams of a drug, and it has a bit more of an effect.
Yeah.
And then slowly I get to like 5,000 milligrams of a drug, and it's probably not going to have that much more effect than 1,000 milligrams. Is it?
Okay. Yeah. So in that case, it looks like this. No, hang on.
Yeah, exactly. Sort of thing. So it is the typical way to draw it is something. I'm just going to be pedantic here. Is it probably no drug means no response, right? So
Yes.
You've got to cross.
Okay. Got to cross. Yeah. 0,
It
0.
looks a bit like that.
Yeah. Fine.
So that's the dose response curve, and that's all the useful information that we want about drugs sits in this bit here. So that's where like your effective dose of the drug comes in, your ED50. That's where all sort of the information about your therapeutic index comes in, and it's quite difficult to extrapolate information from that portion of a curve because it's so steep, which is why we switch it to the semi-logarithmic plot, because if you put a log of the x-axis for a rectangular hyperbola, then it gives you a sigmoid shape curve, and then the useful information about the drug sits in this portion here instead. So that's why we do that.
Yeah.
So that's log dose response curves and dose response curves, and that does come up in the book question at least. I don't know yet about the actual term. Cool. So let's go back to my screen. So curve height is always less for a partial agonist for agonist we decided is true. The scale on the y-axis is logarithmic.
False, the scale on the x-axis is not.
Exactly, yeah. It's shit like that they say they're not trying to draw, they are. Presence of a competitive agonist will shift the curve to left.
No.
Exactly. So what does a competitive agonist do?
Sits on the receptor and prevents the agonist from creating an effect. So, which means that it's shifted to the right, because if you imagine so the dose is on the x-axis. So if you do a competitive agonist, you're going to need more of the agonist to get an effect. Therefore, the shift is to the right.
Absolutely perfect. Yeah, 100% perfect. Absolutely. So yeah, presence of a competitive antagonist will shift the curve to the left, as will a partial agonist with high doses of a full agonist. They will both shift the curve to the right, not left. Curve height represents potency. Everyone's agreed, that's great. It doesn't, what does represent potency?
The
Activity?
so what I think what that graph is showing is intrinsic activity. But potency relates to the dose required to generate it.
On the graph, what represents potency? So this is your log dose response curve.
Is it the greater
the position of the curve? It's the position of the curve. So it's your ED50 is what we call. So effective dose of 50%. So here, effective dose 50%. So 50% of your response. How much dose you have to achieve 50% of that response? Moves to the left or right, and that represents potency. So a less potent drug, you have to give more drug to get the same effect, right? So the dose has to be higher. A less potent drug, sorry, more potent drug, you have to give less drug to get the same effect. So it becomes shifted to the left.
So does height represent intrinsic activity?
So exactly, height represents intrinsic activity. So agonism, partial agonism, antagonism. Cool. What else did we have on here? So curve height represents potency. So no, we said the position left, right, shift of the curve represents potency, and the curve shape is hyperbolic. Not true for the log dose response curve, but it is true for the dose response curve.
Yeah.
And so just be clear in questions which ones they're talking about, because they may ask you questions about a dose response curve where everything will be true except for like the shape of the curve.
Yeah.
So ED50 will still be moved to left or right depending on potency of the drug, but it just would look like a different shape.
Yes.
Cool. That's all I've got. Thanks so much for tuning in and for coming along. Really, really appreciate it.